4-4 is about adding and subtracting like fractions. So we'll start with ones that have the same denominator. Then we'll learn at the end of this section how to start getting a common denominator. And then in 4-5, we'll actually do the math with the common denominator. So this first thing just shows you, if you have the same denominator, just write that denominator once and then do the math with the numerator. So this was a plus c, so it's a plus c up there. If you have the same denominator, write it once, but then do the math with the numerator. A minus c, okay? It won't be too bad if it's just straight addition, but what gets tricky is that they're going to still use all those rules of integers. So a negative plus a negative plus a positive, and all that kind of stuff will get tricky. So let's start with the first one. Do you guys agree that the denominator is 13? So it'll stay 13. And then what's 6 plus 2? 8. You're done. Do you guys agree that the denominator is 8x? What's 5 plus 1? 6. Before we circle that and get done too quickly, though, we have to keep in mind that these might potentially reduce. So I'm actually going to rewrite this as 2 times 3 over 2 times 2 times 2 times x. Here I didn't worry about it because 13 is prime, okay? So I know 8 is not going to cross out with 13. But what do you notice here? A factor of 2 happens. So we're left with what on top? 3, and then 2 times 2 is 4 times x, 4x on the bottom. So that's something we kind of have to keep in mind, like after you do the math, so after you do the addition or after you do the subtraction, your answer might reduce. One way, my math lab's nice, they kind of hint at that, okay? So if we put 6 over 8x into my math lab, I will say, although your answer is correct, it's not completely simplified. So it kind of hints at you like, oh, I did the math right, I still need to do that breaking down and simplifying, all right? Here, don't get scared by 3. They're all the same denominator. So what's our denominator going to be? 11. 20 plus 6 is 26, plus 7, 33. But again, keep in mind it might reduce, right? So what's 33 split up as? 3 and 11, but why does that help us? Because the 11s will cancel out. So our final answer is just 3. So basically, if these were pizzas or cookie cake cut into 11 slices, you know, we had 3 full cookie cakes there when we added up all those slices from each of those. Are there any questions there? Pretty straightforward. All right, we're going to do the exact same thing, but with subtraction, all right? So here, the common denominator is 12, so our denominator is going to stay at 12. What's 11 minus 6? 5. Will that simplify any further? This should say subtract. It will not simplify because 12 will break down to 3 and 4, right? But there's no 5 hidden there, so that is done. What about over here on number 5? What's the denominator? 15, but what's 7 minus 2? 5, and that's going to simplify, okay? So 5 is just 5, but what's 15 break down as? 3 and 5. So this is where you have to be careful because everybody notices that the 5s cancel out and the 3's left, but where does the 3 remain? On the bottom. So how do we show that it's on the bottom? We need to do 1 over 3 like that. Because remember, I don't teach it that way, but when we cross it out, 5 over 5 is a factor of 1, right? All of these things that we cancel out is 1. So 1/3 is your answer there. All right, that's the first 5. Are we doing okay? All right, so where it'll get a little tricky is when we get to just the integer rules, okay? But keep in mind, when you add a negative plus the positive, are you really adding? No, you're subtracting. So this is going to be, hold on, let me write it like that, negative 8 plus 4 over 17, okay? So I'm showing you kind of what we need to do. So 17 is the common denominator, and we need to focus on negative 8 plus 4. When you add a negative with a positive, you're really finding the difference, right? What's the difference between 8 and 4? 4. Is it going to be a positive 4 or a negative 4? Negative because he's negative, right? So our answer is negative 4 over 17. All right. So you kind of just focus on that numerator. It's just kind of like chapter 2 stuff right there. All right, this one's kind of interesting. What's the common denominator on this one? 5. And then what are we going to have on top? 2 minus 7y. 2 minus 7y. Can we go any further? No. So if you remember back to last Thursday when we learned about 3.1 and like terms, This is $2, take away 7 yo-yos. What do you have? $2 and you're in debt, 7 yo-yos, right? They are not like terms because they don't have y's, both have y's, so you just stop. That's all you can do. Now, if that was a 2y minus 7y, you could do the math there, okay? So they have to have that same variable. How's the front page? Is that okay so far?
So basically you're saying they have to have the same variable to...
Combine them.
Okay.
In order to combine them, they have to be like terms. All right, last one, guys. I am going to rewrite this, and as I rewrite it, I'm going to rewrite them as addition problems, right? Whenever you see subtraction. So I'm going to write one giant fraction, and what's the denominator of that one giant fraction? 11. So we're going to have 4 plus a negative 6 plus a negative 3. Is that okay? 4 plus the opposite of 6, which is a negative 6, plus the opposite of 3, which is a negative 3. If you don't need to do that, if you can do 4 minus 6 minus 3 in your head, do that. That's fine, okay? So I'm going to just take this a little bit at a time. Let's focus on these two. 4 plus the negative 6 are opposite signs, right? So what do we do with opposite signs? We subtract them. What's the difference between 6 and 4? 2. Is it going to be positive or negative? Negative. So we're going to have a negative 2 plus a negative 3 over 11. Is that okay? So we've taken a set of 2, 4, negative 6, and combine it to make negative 2. At this point, what do we do when they have the same sign? You add them and give them the sign they share. So what's 2 plus 3? 5, so it's going to be negative 5 over 11. But like I said, if you can just do that in your head, 4 minus 6 is negative 2, minus 3 is negative 5. That's fine too, okay? So just do what you need to do to get that top answer. All right, the last thing here before we get into our square is just plugging them in, right? So we have x plus y, where x is negative 10 over 12, plus y is 5 over 12. So do you guys agree that they have the same denominator? Yeah. So what's our common denominator going to be? 12. And what's negative 10 plus a positive 5? When you add opposites, you're really subtracting. So what's the difference between 10 and 5? 5, what's our answer going to be? Negative. And guys, just think about it. You guys all answered that pretty easily and quickly, and that's stuff you struggled with a couple weeks ago, right? It's kind of cool to see the growth that you guys have when it comes to these integers, these things that you struggled with before. You're able to validate that you know them now. All right. So then, now that we know how to add fractions, where in the real world, real life, would you see fractions? Say you have a plot of land that's a square, and it's 3/20 of a mile on every side. So let's go ahead and label that. And you're going to want to put a fence up, okay? How much mileage of a fence do you need? Well, how do you find perimeter? What do we have to do? Add all the sides. Right? So we're just going to have 3/20 plus 3/20 plus 3/20 plus 3/20. And again, don't get scared by how many things we're adding because they all have the same denominator. That's nice and easy, right? So what's our common denominator going to be? 20. And then we'll just do the math on top. 3 plus 3 is 6, plus 3 is 9, plus 3 is 12. 12/20. You put that into my math lab and it'll give you a red X. It'll say, although your answer is correct, it's not completely simplified, okay? So let's go ahead and break this down. How does 12 break down on a factor tree? 3 and 4. And then how does 4 break down? 2 and 2. So 12 is 3 times 2 times 2. Is that okay? How would 20 break down on a factor tree? 10 and 2, 4 and 5, it doesn't matter, right? Ultimately, then you'd have to break down the 10 to get a 2 and a 5, or the 4 to get a 2 and a 2. So you get a 2 and a 2 and a 5, right? 2 times 2 is 4, times 5 is 20. What do you guys notice that they both share? 2 sets of 2, aka 4. If you can look at 12 over 20 and know that 4 goes into both and reduce it right there, that's fine as well, okay? So what's our answer as far as how much fencing we'll need? We'll need 3/5 of a mile of fencing. It's a lot of fencing. They're kind of just rolling everything back, and like they're not letting you forget what perimeter is. Perimeter, add up all the sides, right? Last one here, guys. A jogger ran 13/4 miles on Monday and then 11/4 miles on Wednesday. How much further did he run on Monday than on Wednesday? Whenever you have to compare, what math do you do? How much older am I? What would you do with my age? Subtract, okay? So anytime you compare how much more, how much further, what's the difference, this is always going to be subtraction when you're comparing. Okay? So when you're comparing, always subtract. And we're going to take the bigger, 13/4, minus the smaller, 11/4. What's the common denominator? 4. What's 13 minus 11? 2. And what can we do with this, guys? The 2 will stay a 2, but what does 4 break down to? A 2 and a 2, okay? And that helps us because we can knock out one of those 2's. How do we show that 2's on the bottom? We need a 1 on top. So he ran a ½ mile further on Monday than he did Wednesday. Is that okay? Let's see. All right, so then they say, they kind of like pat you on the back and say, good job. You know how to add and subtract when they have the same denominator. Life would be all rainbows and kitty cats and gumdrops if all our fractions we ever added had the same denominator, right? But that's not the case. And so what they say is, we need to learn how to make denominators look the same, okay? So that's when we find the LCD, the least common denominator, okay? It says the least common denominator of a list of fractions is the smallest positive number divisible by all the denominators. So all the denominators need to go into it, but we want the smallest one. We don't want them to get too large. Finding the LCD of a list of fractions using multiples of largest numbers. So what they're going to do is they're going to teach you 2 different ways. Okay, so the first way is write the multiples of the largest denominator first, starting with the number itself, until you hit a multiple that the other one goes into. Okay, so looking at this, we're not even worried about the numerators right now. We're just finding the LCD. Okay, we're only going to focus on the denominators. Which one is the largest denominator? 8. So we're going to list multiples of 8. So multiples of 8 just means you're adding 8 repeatedly, or you're multiplying 8 times 1, 8 times 2, and so forth, okay? So what we're going to do is we're going to do all these multiples of 8 until we hit a number that 6 goes into. That will be our LCD, all right? So you start with 8. Can 6 go into 8 evenly? Nope. What's 8 times 2? 16. Can 6 go into 16 evenly? No. What's 8 times 3? 24. Can 6 go into 24? Yes. So 6 can go into 24. So what does that mean? It means 24 would be our LCD, okay? It means that's the smallest number that both 8 and 6 go into. All right? They don't want us to convert. They don't want us to do anything. They just say, hey, if we were going to convert these slices, one cookie cake's cut into 8 slices, one's cut into 6, we'd have to cut each of them into 24 slices so we can compare the amount of slices we have, all right? Let's do the exact same thing on 13. We have 25 and 30 that we're focusing on. Which one's bigger? 30, so we're going to do multiples of 30. So you start with 30 itself. Does 25 go into 30 evenly? No, it's almost the same size, right? 30 times 2, 60. Think quarters. Do you have an even amount of quarters if you have 60 cents? No. So what's 30 times 3? 90. Does 25 go into 90 quarter-wise? Think quarters. Can you get 90 cents with just quarters? Nope. So what's 30 times 4? Well, I heard it. What did you say? 120. Can you have an even amount of quarters and have 120 cents? $1.20? No. What's 30 times 5? Add another 30 to it. What do you get? 150. Can you that works, right? Because think if you had $1.50, you can have $1.50 with just quarters, right? So 25 goes in. So what's that mean our LCD is? 150. Does everybody see where I'm getting these numbers? I'm just adding 30 to it every time, right? 30 plus 30 is 60, another 30 is 90, another 30 is 120. And then anytime 25, I just think quarters. And so if you had 30 cents, 60 cents, 90 cents, or $1.20, you couldn't have that with just quarters, right? It's not until we get to $1.50 that you could have 6 quarters. Okay, so that's one method they teach you how to do LCD. Another method down here, so I'm not going to like force you to know both, okay? I'm going to teach you both, and you get to choose which method you prefer, all right? So let's look at this next one. Write the prime factors of each denominator first, okay? So we're going to do our factor trees for each denominator. And then once we do that, we're going to circle all the different prime factors, and the greatest number of times that occurs, it has to be in there. I'll show you. We'll actually just do it, okay? So we're just focusing on our denominators again. So we're going to do a factor tree for 40. Were there any two numbers that multiply to be 40? 4 and 10. But then how does 4 split up? 2 and 2. And then how does 10 split up? 2 and 5. Okay? So here's my primes. We're going to worry about those in a second, all right? Then we're going to go to 108. That's a big number, okay? But does anybody know their 12 times tables? No. It's 9. Look at you. That's awesome. Okay, so it's 9 times 12. Say you didn't know that. It's even. So what do we know goes into it for sure? 2, right? And so we could figure out how many times 2 goes into it by doing long division. All right. How does 9 split up? 3 and 3. And how does 12 split up? 3 and 4, but why does that what happens there is 2. So when it comes to doing the LCD, guys, we have to represent every number in each denominator, okay? So what does 40 need? 40 needs 3 2s and a 5. So guess what we're going to start with? 3 2s and a 5. Then we go to 108 and we say, well, what does he need? He needs 3 3s. Do we have 3 3s yet? No, so guess what we have to add on? 3 3s. And then he needs 2 2s. Do we already have 2 2s? Yes. So we only had to add this new one. So basically, if a number repeats because it's from one number, you need all those numbers. Like we can't get 40 without 8. And how do we represent 8? With 3 2s, okay? But if you go to your next denominator and they share those factors, you don't need to write them, okay? So our common denominator is going to be this product. It's kind of big, so I'm going to take my time here. Let's look at what's going on. What is 2 times 2 times 2? 8. And then we'll do times 5. And then what's 3 times 3 times 3? 27. So I'm kind of just grouping them just to make the math a little easier, okay? What is 8 times 5? 40. So guys, we have to do this multiplication to figure out what our LCD is. So I'm just going to go over here to the side. 40 times 27. 7 times 0 is 0. 7 times 4 is 28. Do your lattice or whatever you need to do to make that multiplication happen. Then when I go to 2, I got to shift over. So I'm going to put a 0 there. And I'm going to shift over to 2. What's 2 times 0? 0. What's 2 times 4? 8. So when it's all said and done, we get 0 plus 0, which is 0. 8 plus 0, which is 8. And then 2 plus... You guys get 1,080? Yeah. Woo! That's a big guy. Okay? Why this might work a little bit better is because even though it's a little bit more time consuming, thinking of multiples of 108 might be hard, right? Like 108, 216, where do you go from there kind of thing? And you'd have to just keep going. Where here, we already know how to break down numbers. We've been doing that since 4.2. So the whole thought here is that we know how to break down numbers so we can build our LCD using all those factors. So the whole idea is, here's our first denominator, and then here's our second denominator, right? We needed 3 2s and a 5. There it is. And then we needed 3 3s, 2 2s, and a 5. There he is, okay? But we didn't make it too big, right? If we put all those factors in, it would have been a lot larger. So we shared the 2 2s. Let's try that again at the top of page 4, okay? They try to scare you by throwing 3 at you, but that's fine. I don't care. I'm not scared. All right? 20, how do we break 20 down? 2 and 10. How does 10 break down? 2 and 5. Is that okay? Then you go to 24, and you just do the same thing. What are any 2 numbers that multiply to be 24? 2 and 12. How does 12 split up? 4 and 3. How does 4 split up? 2 and 2. And then we go to 45. How does he split up? 5 and 9. And then 9 splits up as 3 and 3. So remember, we're just focusing on the ends of the branches. 2, 2, and 5. 2, 2, 2, 3. 5, 3, 3. Right? Don't worry about 10 or 12 in there. So we're going to move to our LCD. Our LCD needs every denominator completely. So let's start with this first denominator. What do we need for 20? 2 2s and a 5. Then we move on to 24. What does he need? 3 2s and a 3. How many 2s do we already have? 2. So how many do we need to add on? Just one more. Do we have a 3 yet? No. And then we go to 45. What does he need? A 5 and 2 3s. Do we have a 5? Do we have 1 3? So what do we need to add? And the whole thought process there, guys, is that in that concoction of primes, we should be able to see all of our denominators, okay? So what do we need for 20? 2 2s and a 5. There he is, right? What do we need for 24? 3 2s and a 3. So there's 24. Do you see it? And what do we need for 45? A 5 and 2 3s. So the whole idea is like in that kebab little stuff, okay? We have every denominator represented, but we don't overload it too much, right? We don't put 1, 2, 3, 4, 5 2s and 2 5s and 3 3s, right? We don't want to overload it. So at this point, guys, we're just going to multiply what we have. 2 times 2 is 4. 4 times 5 is 20. 20 times 2 is 40. Let's just stop right there, okay? So I got these, right? So 2 times 2 is 4. 4 times 5 is, did I do that right? 20. And then 20 times 2 is 40. And then what's 3 times 3? 9, right there, okay? So, you kept going. That's fine, too. So she can do 40 times 3 is 120. 120 times 3 is 360.
I have to like break all of them down.
That's fine. Here, what's 4 times 9? Don't worry about the 0. What's 4 times 9? 36. And what do we add on the end? 0. So this is 360. So the smallest number that 20, 24, and 45 go in is 360. And that's a lot smaller than if we took 20 times 24 times 45. Like, that would be a huge number. So by breaking them down, we can see what they share. And again, it might be a little bit easier because if we did the other method, we would take 45 and do multiples of 45. But I'm not comfortable with numbers that 20 and 24 go into. You know what I mean? Like, we do 45 and then 90, and I'm like, I don't know if 20, so by breaking them down, you're kind of the no-fail method. All right, so in this one, do we need a factor tree for y? No, because how does y split up? He's just y. And then do we need a factor tree for 11? No, because how does 11 split up? He's just a 11. So when you go to build your LCD, remember you need both denominators represented completely. So what do we need for the first denominator? A y. What do we need for the second denominator? An 11. So guess what our LCD is? 11y.